Hey guys, sorry I'm not able to be there today, but hopefully you had a good discussion about your results. I want to take a few minutes here to kind of summarize what I hope you've already talked about in the first piece of class amongst your groups and some of the relationships that you saw, and then we'll move into the kind of why and what's going on. So let's start with, let's see. That works. Let's start with the effect of initial velocity on final velocity. And hopefully you found that it was a more or less direct relationship. Linear, proportional, because I hope that you see that if the initial velocity is 0, then clearly the final velocity is going to be 0 because they're not going to actually collide. But as that initial velocity increases, the final velocity increases as well, and it would continue to increase as much as we could continue to increase that initial velocity. The other two, though, maybe are a little bit less clear. So let's look at the mass of the first cart, so the mass of the cart rolling down the hill, and that was probably more of a curved relationship, so something maybe like this. And depending on how you graphed it, if you didn't factor in the beginning or the extreme cases, then you might have tried to put some type of linear relationship on it, and it would have had some significant positive y-axis. But what we again need to think of, and in a lot of these situations I'll ask you to think about the extreme situations, right? And in this case, the two extremes, the first one would be 0 mass, and if there's 0 mass, then that shouldn't change the final velocity in any way. If you have your theoretical 0 mass car rolling down the ramp and colliding with our regular car, it's not going to change the velocity. So we can consider that 0 point, and if we do that, then I think it makes the slope a little bit more clear, or the change in the slope a little bit more clear. And then if we consider some other extreme, some supermassive object, especially, let's take it outside of the classroom. Consider driving down the road in your car and you run into a bug. The bug is our second cart. The car is the first cart. How much effect does that collision actually have on the final velocity? And the answer is very little. It doesn't slow the car down. It doesn't change the car's velocity much at all. And so we actually end up having this upper limit that is the crud. I just realized I mislabeled my axes. I am very, very sorry. I did it over here too. Trying to do this too quickly. Our independent variable should always go on the x. So our VF, and hopefully you guys caught that before I did. So M1. So as our initial mass increases, our final velocity gets larger, but incrementally so. And then this upper limit that we see here is the initial velocity. And so as our mass increases, we see that our final velocity gets closer and closer and closer to the initial velocity until at some point we get to the extreme case, and when that's the case, the final velocity is going to be the same as the initial velocity. Okay. I can't believe I did that. All right. Pressing on. Let's go ahead and make our third graph where we have our dependent variable, the final velocity, on the y-axis where it belongs, and our independent variable, the mass of the second cart where it belongs. And in this case, we should have seen a decreasing or almost inverse function between the mass of the second cart and the initial velocity. And actually this one, again, if we consider the extreme cases, this one should actually have a y-intercept that is the initial velocity, because if the mass of the second car is 0, then that first car is going to roll down. There'll be no collision because there's no mass, and so the final velocity will be equal to the initial velocity. As that second mass gets larger and larger and larger, our final velocity should again approach 0. We consider the opposite of our previous extreme. We have a bug flying down the road and it runs into a stationary car. There's going to be no change in the velocity of the stationary car, significant change in the velocity of the bug, probably to the extent where it might not survive. So these are the three variables and their relationships that we looked at, tying together the masses of the two carts, the initial velocity of the first cart, and then the final velocity of our system. Now we did kind of ignore, and intentionally so, the velocity of the second cart and any impact that might have on the system, but we'll talk about that in a little bit. So let's really quickly look at what you did. I'm going to show you a couple of videos. I gave the cars a little bit of a push rather than have them roll down a ramp, but the result is the same. So let's see if we can get this to play. Beautiful. So what we saw here is the first cart roll along at some velocity, collide with the second cart, they stick together and move off in the same direction as the initial velocity of the first cart. This is basically what you guys did in your lab. Now if we look at the graph, and this is a graph of velocity, that's not going to show up well, that shows up better, velocity on our y-axis and time in seconds on our x-axis. And what we should notice, so the blue line is the velocity of the first cart, and we can see that negative is actually to our left. Not a big deal, right, because velocity is a vector. So our velocity is negative I think that's 0.5. This line right here is 0.5, so it's like 4.5, negative 4.5, so it just means 0.45 rather to the left. After the collision, we see that the speed of the initial cart slows down, the speed of the other cart increases. They meet here, and because they're stuck together, they of course have to move off with the same velocity. They're a single unit, so they're going to have the same velocity. What you should notice is the magnitude of that velocity, and we're going to ignore friction, right? We see there's a little bit of a slope here because of friction. There's a little bit of a slope here because of friction. But if we look beyond that, if we ignore that particular piece of it, we should see that the velocity of the system after is about half the initial velocity. Okay? Interesting thing about that is that our mass of our system after the collision is about twice the initial mass of one cart, because we have two carts that are combining and moving off as one. So there's probably something there. Now this next scenario, I've put magnets between the carts and they repel. So the cart on the right is going to collide with or approach the cart in the middle, and the two are going to repel each other. So instead of sticking together, they're going to repel. So let's take a look at that. And then let's take a look at our graphs. So that was kind of cool, right? I think so. What we should notice here is that after the collision, cart 1, our initial cart, we'll put over here, came to a stop. Cart 2, this guy right here, moved off in the same direction that cart 1 was initially traveling with basically the same speed. And we can see that if we focus on our graph. We can see that cart 1 started with some initial velocity here. This part right here in the middle, I like this part. I think it's cool. That's where the interesting stuff happens. That's the collision. And the interesting part there, I think, or one of the interesting things, is that it's not instantaneous. Here we can actually recognize the time over which that collision happens. But within that time, two big things happen. Our cart 1 slows down. So it starts here, it slows down and comes to a stop. At the same time, cart 2 speeds up, and it actually speeds up to the same speed or the same velocity that cart 1 had prior to the collision. So that velocity is going from cart 1 to cart 2. Couple more situations I want to look at here. This one we're actually now including some initial velocity of cart 2. We want to look at this one. We got two more situations to look at, and then we're going to kind of bring it all together. So let's start by watching what happens when the two cars move towards each other and bounce off. Okay, let's watch that again. Oh, we can do slow-mo. Oh, I hope this shows up right. Slow-mo, they're coming in, they interact, and they bounce off. And then we're gonna zoom in on the graph. Okay, so again, our blue line is the cart moving to the left, our red line is the cart moving to the right. Notice that within a reasonable approximation, their speeds are the same, but their velocities are different. So the magnitudes are the same, but one is positive, one is negative because they're moving in opposite directions. During the collision, right here, we see the blue line, the cart moving from the right to the left, slows down, comes to a stop, and then increases its velocity up to what we might notice is the same velocity as cart 2. Cart 2 does the opposite. And so it's almost as if those velocities are switching cars. All right, so cart 1 comes in with some negative velocity, it leaves with a positive velocity equal to what cart 2 had. Cart 2 comes in with a positive velocity, leaves the collision with a negative velocity that is more or less equivalent to what cart 1 had prior to the collision. Hey, that's a lot, but they're bouncing off with the velocity that the other cart had. Next one we have is a situation in which our two carts start out moving with no velocity. So actually not moving. So they each have an initial velocity of 0. They're right next to each other. And then the gray cart on the right has a small plunger that when I hit the button, it's going to extend, and they should move apart. So let's observe what happens. Okay, so the plunger extends and they move apart. And if you look closely, you should notice that their speeds are more or less the same. And if we zoom in on our graph, what we should see is that they are actually beforehand, this is before the plunger releases, they both have a velocity of 0, and then they go off with speeds that are more or less the same but in opposite directions. Okay, now in all of these situations, we've just used the same two carts, but what happens if we increase the mass of one of the carts? And you guys, a couple groups looked at changing the mass and what effect that had. So let's take a look at that. Okay, so here, same situation, we hit the plunger, but the mass on the left, or the cart on the left, has twice the mass. Notice what that does to the velocity after the collision, and we'll call this a collision. Even though they're not running into each other, they're still interacting with each other. So then if we look at the graph, what we may notice here is the cart that has twice the mass has roughly half the velocity, half the final velocity. Okay, so we're moving off, one cart's moving off to the right, the smaller one, and it has twice the velocity. The more massive cart is moving to the left with roughly half the velocity. Okay. So those are all pretty interesting relationships. And what we find is that we now have basically 4 different variables, or actually even more than that. But we have initial masses, initial velocities, final masses, and final velocities. And this quantity that ties mass and velocity together is a new quantity for us that we call momentum. And momentum is simply the product of mass and velocity. And conceptually, we can kind of think of it as how hard it would be to stop something, right? Because it's affected by both the mass and the velocity. If we have something that's really, really massive, like a tractor trailer, even if it's moving along the road really slowly, you're probably not going to be able to stop it very easily. On the other hand, we might have something with a very small mass, something like a bullet, but if that bullet is fired out of a gun, it's going to be moving really fast and it's going to be really hard to stop. Now, because mass is scalar and velocity is a vector, and we can show that it's a vector with a little arrow over it, a scalar times a vector gives us a vector. So momentum is a vector quantity, and that's going to be important to remember. So again, vectors mean direction matters. So if we go back to any of those previous systems that we looked at, what we might notice is that that product of mass and velocity for the system stayed the same. So when we had one cart of some mass colliding with another cart of the same mass and they stuck together, they moved off with half the velocity. So the mass doubled, the velocity was cut in half. When the cart collided and the second cart just bounced off, in that case, the mass stayed the same, so the velocity stayed the same. And so this idea, this principle, is what we call conservation of momentum. And you can actually put this in the box at the top of the front page of your packet. This is our new fundamental principle. And it's one of the most important ones in physics. Momentum is a quantity that is really and truly conserved across the universe. So if we write out this idea of conservation of momentum, the total momentum in a closed system is a conserved value. Now, if you look at that a little bit more closely, first, a closed system. A closed system is one in which there are no outside forces. So, in our cart situations, even though the carts are exerting forces on each other, those, if we consider both carts as our system, then those forces are internal, and therefore they don't affect the momentum of the system. Now, what you would have noticed, and what we said to overlook previously, is that slope in our velocity graph, and that slope represents acceleration, and we saw that the speed of our carts was in fact decreasing, which, if we have a change in velocity, that means there's a change in momentum. Well, we weren't taking into account the surface of the table, and that particular object is exerting a force of friction, which in this case then is considered an outside force. So the reality is that our closed system isn't quite as closed as we would like. Now the other part of this then, conserved value. Conserved means that something is saved, right? Conservation of the rainforest, we're trying to save the rainforest. In this case, we're conserving momentum. So our momentum does not change. A little bit more mathematically, that looks like this. Our initial momentum is equal to our final momentum. And then we can expand this out and talk about the initial momentum of all of our objects in the system. So in this case, we have two carts. Each one has some momentum initially and finally. And we can observe that that doesn't change. We can start making some calculations, which we'll do a little bit later on, and we can see that that total momentum doesn't change. So let's look at a new way to help us visualize and describe this. We're going to use what we call if charts or momentum bar charts. Our I stands for initial. Our second F stands for final. We'll talk about the first F here in a little bit. So let's consider our system where we have two carts and they bounce off of each other. For our bar charts, the y-axis is going to represent the velocity. Along the x-axis, we're going to indicate our objects, but it's really going to tell us a little bit about the mass. And so if we have two carts, we're going to identify our two objects, cart 1 and cart 2. The width of our bars for each object is going to represent the mass. So the wider the bar, the greater the mass. So our initial scenario, our initial system, our first cart has some velocity. So we're going to draw our bar up to that velocity. And what we should recognize here, hopefully, is that, and we can do this as quantitatively or qualitatively as we want, but if the width of our bar represents the mass of our object, and the height of our bar represents the velocity of our object, then the area of our bar is equal to mass times velocity, which is then equal to momentum. So in this way, we can indicate graphically the momentum of the system pre-collision. If we then create a second graph showing our final situation, here's cart 1, here's cart 2. In this case, cart 1 collides with cart 2. Cart 2 goes flying off and cart 1 comes to a stop. As we noticed, cart 2 leaves with the same velocity that cart 1 came in with. Assuming it's the exact same mass, its width is going to be the exact same. And so our final momentum, again, is going to be mv here. Because the mass and the velocity are the same for each, the areas of both of those bars should be the same. And so we see that our initial and final momentum are identical. Now let's take a look at the situation where they stuck together. So we have V, we have M, we have cart 1, we have cart 2, we have some initial velocity, and so we have some momentum. We noticed, to our amazement and joy, that the velocity after was basically half the initial velocity. And from our diagram, hopefully we can see that our total area is still going to be the same, meaning that our total momentum before and after is still the same. So initial and final. So these are great, right? These are these nice, clean, closed system situations. Initial momentum is equal to final momentum. But what happens when we have an open system? What happens if, for instance, we only determine that we want to focus on one cart? So if we're just looking at one cart, we might, in a case where they collide off, so let's go back to the case of our colliding off. So cart 1 is moving with some velocity. And we're not worried, we're not focusing on cart 2. So cart 2 is not part of our system, it's just cart 1. So cart 1 starts with some momentum. If we look at the after, what we might see is that there's no momentum. So, oh my goodness, there was a change in momentum, which we just said the momentum of a closed system doesn't go away. We don't lose it. It's conserved. Well, this isn't a closed system. And this is where our very first F in our if comes in. Our first if is where we take into account any outside forces, also called external. Okay, so if our system is both carts, then the forces between the two carts are internal. If we're only looking at a single force, then the force on that cart is an external force. Now again, because forces and velocities and accelerations are all vectors, the direction matters. So when cart 1 hits cart 2, it exerts a force on cart 1, or on cart 2 rather. Because Newton's third law, well, not because of Newton's third law, but Newton's third law at least explains that forces come in pairs. And so if cart 1 exerts a force on cart 2 must exert an equal and opposite force on cart 1. Now, if we're calling the direction that cart 1 is moving in the positive direction, that means it's exerting a force on cart 2 in the positive direction, which means that the force on cart 1 is in the negative direction. So we're going to draw a force, and as we saw on our graphs that we looked at in our situations, that acceleration that's caused by the net force is not instantaneous. It happens over some time. And so we're going to graph force versus time. And again, at this point, we're strictly qualitative, but we will certainly do more in the quantitative realm with this. But what we should notice is that I have conveniently drawn the force versus time graph to look like it has the exact same area as the velocity versus mass graph. And that's intentional. What you will also notice is that, as we said, it is a negative force. And so if we were to take area 1, our velocity mass, and we were to add it to area 2, we would get a value of 0. What we should then notice is that the momentum of cart 2 after the collision is 0. Okay, so what is this force and time area telling us? It's telling us the change in momentum. So while we just did it very qualitatively in a graphical form, what we find is that force times time, and we're going to say average force. So average force times time is equal to change in momentum. In physics, we give this idea of change in momentum a specific name that we call impulse. An impulse is symbolized with a capital J. So we will see the equation J equals F average times T. And again, because we have a vector times a scalar, our product is a vector. So impulse is a vector quantity. And this is when we're looking at specific individual objects. So the total momentum of a system, of a closed system, may not change, but the total momentum of individual objects, or unclosed, open as we call them, the opposite of closed, systems, may change. Okay, so with that, I'm going to ask that you watch the notes video for Monday, and then on Monday we'll have a couple of things to help us understand this better to work on as well. Other than that, have a great Thanksgiving break, and I'll see you next week.